Oh, we have a marvelous lecture today, guys. Just marvelous. And very important. One of the most important lectures from chapter 4 is coming about. Are we ready for it? All right, guys, let's make this recollection. So you remember that what is expected value, right? And what is an expected value of a random variable, and what is expected value of a function of a random variable? Yes? No problem there? And you remember that you can calculate it in so many different ways, right? So we spoke of something like, for instance, if you have 3 possible outcomes, well, let's have it 4 possible outcomes. So you have outcome 1, 2, 3, and 4. Let's say each of them is equally likely. So the probability of each is 1/4. And same for all the other events. So that's my sample space S. Then I can generate a sample space star where what's happening to 1? 1 is mapped to x1. Yeah. 2 is mapped to x2, which in this case happens to be the same as x1. So that would be x2. 3 is mapped to x3, and 4 is mapped to x4. So that this x that does this expression is a random variable, right? So let's say 2 and 1 were mapped to the same event, so that means x1 is the same as x2, right? So that's the identification that just happened here. So what can we then we can describe all sorts of further relabelings, right? So further relabelings would be, for instance, this can be relabeled as g of x1, and this can be relabeled as g of x2, g of x3, g of x4, right? So what is a random variable? It's simply a relabeling of the individual outcomes in my sample space. That's it. What is a function of a random variable? It's a relabeling of a relabeling. Does it make sense? So that's all that is. Now, how can you calculate the expected value of a function of a random variable? You can do that in so many ways. So that's just a payoff. So for instance, we gave this example where maybe I can kind of modify it and say, so the probabilities of the previous events are 1. Then let's say x is x of a value. X of 1 equals to x of 2, as we said, and that would equal to maybe the number 3. And maybe x of 3 will equal to 0, and maybe x of 4 will equal to -1. Okay, so that's a random variable. Now I can describe something like a function g of x, which well, maybe what it does is just multiplies x times 2, right? Multiplies x times 2. So I can calculate the expected value of g of x in many ways, right? I can calculate by definition what are the values that g of x can take. So g of x can equal to what numbers? It can equal to the number 0, 0 times 2, right? It can equal to the number -2, and it can equal to the number 6. Those are the values that G can equal, yes? And one way to calculate the expected value, so if I call this Y, I can say the expected value of Y is simply 0 times the probability or that G or that Y is equal to 0 plus -2 times the probability that Y equals to -2 plus 6 times the probability where Y is equal to 6. This is by definition. So far good? By definition, and we know those probabilities. So the first part is just 0. Second part, it's -2. When is Y equal to -2? Y is equal to -2 when X is equal to -1, and the probability of X being equal to -1 is 1/4, right? So it's -2 times 1/4 plus 6 times the probability that Y is equal to 6, which means X is equal to 3, right? And if X is equal to 3, the probability is this plus that, which is 2/4. So it's 6 times 2/4. So the result is simply -1/2 plus 3, right? That's one way to calculate the expected value. Another way is to just add up the expected value based on the individual outcomes. So the other way to calculate, we found out the expected value of G of X is to see what's the probability of G of X being equal to 0 times the probability where X is equal to 0 plus G where X is equal to what was X equal to? X equal to 3 times the probability where X is equal to 3 plus G of X equal to -1 times probability that X equal to -1. Yeah, and if you do that this way, you will get the same value, and it's not important which random variable you picked. You understand why, guys? You understand that when you carry out the summation, you can imagine that you have a table, and in this table you have in theory 3 outcomes: the individual outcomes per game of the sample space, and then the corresponding labelings that you have, the labeling in terms of X and the labeling in terms of G of X. And you can use you can sort by any one of those columns. Yes, you understand what I mean, guys? So let's see if you have questions afterwards. Make sure, guys, that you truly understand it, because it's extremely important idea here. Here is that what we have just summarized. So X is a random variable. It maps the sample space S to an induced sample space S star. And this is the result. The image of S is S star, so that means it's onto. And the probability that X is equal to S star is just the summation of the probabilities, the individual probabilities of the outcomes in the sample space that were labeled with the letter S star, with the value S star. Right? So what's the probability that X is equal to S star is just the sum of the probabilities of the outcomes that were labeled as S star. Good, and this is just an illustration of what it can be. In this case, it seems that for this particular S, 3 individual outcomes were labeled as S star, so we add up 3 individual probabilities.
I see. So the formula right above it is what you just did, right?
Yes. Oh, yes. I mean, I just kind of came up with just a ridiculous, just any sort of example. I mean, I covered it. It's hopefully a review if you watched the previous lecture, but if not, you let me know, guys. Okay, we will see in a moment. So this is if S star is in R, then the expected value of X can be simply calculated as this summation, guys, and it's not trivial notation. So it's a summation where S belongs to S, little s in S, of XS, P of S. Do you understand what this means, guys? This is not the definition of expected value of X. This is sorting the expected value based on the outcomes of the sample space. Let me show you the difference, right? So again, let's just use 1, 2, 3, 4. That's my sample space S, and I'm assuming they have equal probabilities. Right, so when I apply some random variable X, that means that a bunch of them are designated by the same value. Yes, so how are they? Let's say if the example that I just came up with, I think 1 and 2, it doesn't matter if I was right or not, they were designated with the payment 3. Okay, now 3 was designated with payment 0 and 4 was designated with the payment -1, I believe. Good. That is an example that I got. So this is, in other words, if I get either 1 or 2, the random variable is displaying 3. By definition, the expected value of X is what? It is if I sort them by order, it's 0 times well, let's do it from the largest to smallest, right? So let's carry it like this. So it's 3 times the probability that X equal to 3 plus 0 times probability that X is equal to 0 plus -1 times the probability that X is equal to -1. That's the definition of the expected value of X, and that would have yielded 3 multiplied by 1/2. Probability that X is equal to 3 is 1/4 plus 1/4, right? Either if I get outcome 1 or outcome 2, I get that result. So it's 3 times 1/2. 0 here doesn't matter. So -1 times 1/4. So -1/4. This is the expected value computed by definition. But you have to remember, what is that expected value? What is it calculating? So what it's calculating, guys, is if you play many games, right? So this is the number of games that you play. So that's the outcomes of the sample space. And this is the value of X that you obtain, the payment. X is the payoff, right? So suppose that you play this game and you got outcome 2, 2, 2, 1, 1, 2, 3, right? So, and onwards. This is a giant table, good? So 2 corresponds to the payment of $3. Again, a payment of $3, again, a payment of $3. 1 corresponds to also a payment of $3. Here is again another payment of $3, and then this is a payment of $0 and onwards, right? This is the X. So what you can do is you can add up. So how many games we had here? This is game 1, 2, 3, 4, 5, 6, 7, right? And onwards. So eventually there is a game end. So what you do is you add up all the payments and divide by total number of games. And the prediction is that if you have played the game long enough, you will see that the number that you're obtaining is that number of the expected value that we produced before. It's this number here, right? 3 over 2 minus 1/4 is going to be the convergent number once you play enough games. Yes? You all see that, guys? But how I obtain this average? Obviously, I can decide to group the second column or the first column. You understand? So if I group by the what I did in this summation here, do you see what is that 3? 3 means that basically what I did is I sorted the second column so that the first thing I see is 3s. So I take 3s, and the probability is the number of times in my games that I received the payment 3 divided by total number of games played. That ratio approaches the probability of getting 3. Do you get it, guys? That probability, so I sorted first, I add up all the payments where I got 3. Then I will add up all the payments where all the games where I got 0, and finally all the games where I got -1. And when I average it, it becomes 3 times the probability of getting 3 plus 0 times the probability of getting that plus -1 times the probability of getting -1. Good. I could instead group by, I could sort this column. I want it to be in order. I want all the ones to be first. Once I'm done with all the ones, I want to begin sorting over 2s. And once I'm done with 2s, I want to sort over 3s. And so on and so on and so on, right? And then 4s. You understand? So imagine that I sort, you all play with computers, some of your computer science majors. So the difference in how we calculate expected values relates to how we sort our table. We are still going to add up only the second column. We are adding up this. You understand? But the order in which we are adding it up is irrelevant, definitely for finite situations, and it's irrelevant for absolutely convergent series in general if you have infinitely many outcomes. Okay, so that means that I am free to carry this addition by different sorts, by either using the sort for column 2 or sort for column 1. And here I use the sort using which column? Can you tell me, please, in my comments? If I say S in S, X of S, P of S, that indicates that I calculate my expected value through sorting which of the 2 columns. Yes, I definitely sort through column S. I saw not enough answers, but for sure it's using column S. Do you all see that? It's very important, guys, for you to see that this is because you see I use not the range of X, but using the domain, right? So the second column represents the range of X. So if I use the domain, it means I'm sorting. I'm saying, okay, pick any particular outcome. And what am I getting? If I get that particular outcome, I get payment X of the outcome, right? X of the outcome is how much what is the relabeling of the outcome, right? And the amount I will get on average is the payment corresponding to the label of S multiplied by the probability. You see why I multiplied by the probability? Because we have this notion of running frequency. If the table is not like I drew it, it has to be a huge table. The bigger, the better. Billions of entries, maybe, right? Over that huge table, the ratio should be tending to the probability, right? The total number of times the outcome S occurred divided by total number of trials should be the probability of occurrence for that particular outcome S. Are you with me, guys? And similarly, the expected value of G of X, I can sort using the column S, using the first column. And I can calculate the expected value this way. This is a hugely important consequence of that result, guys. Look how easy the result if you understand it. If X and Y are random variables over the same sample space, then the expected value of X plus Y, no matter what, is going to be the sum of the expected values of X plus Y. And we're going to exploit this idea over and over again. You see that? Now, why is that the situation? Given any random variable x and any random variable y, I can construct a random variable z, which is x plus y. What's the expected value of z? If I use sorting through the first column, it's z of s times p of s, which is the summation of x of s plus y of s times p of s. I can distribute and multiply the p of s through and separate the summations. And here we have the result. You understand? It just follows by distributing the summations. And I have that this is the expected value of x plus the expected value of y. Okay, and in general, obviously the corollary extends. You can see for any finite addition, in fact, for every infinite addition, as long as convergence holds, this result extends. Do you see that? I mean, there was nothing special about using two events. I can distribute any finite sum. In fact, I can distribute any infinite sum as long as you have uniform convergence, because all that we're doing is rearranging the order by which we're adding. You see, when we're sorting the columns, we're rearranging the order by which we're adding the terms of the series, finite or infinite series. Here is a simple application, guys. 2 fair dice are rolled. Compute, please, the expected value of the sum. Right? What is going to be the average sum that you will be getting on the dice? Okay, Kunyan, thank you. Good. Now the situation can be done this way, guys. You see, I can label x be the outcome on die number 1 and y be the outcome on die number 2. And so the summation is the outcome on die number 1 plus the outcome on die number 2. Agreed? So in particular, what's the sample space? The sample space is of x is just we have a pair of values. We have outcome 1, outcome 2. X is a projection of the first coordinate. Y is the projection of the second coordinate of pairs of values. Do you agree? I mean, in terms of labeling here, you have x of st is equal to s and y of st is equal to t. In other words, y displays the outcome on the second die, x displays the outcome on the first die. Yes? That's our random variable. Now, we know that the expected value of z is the expected value of x plus y. Right? Z is just s plus t. What's the expected value there? Now, the expected value of x, it's just, we know that if we just isolate x by itself, the probabilities will collapse to the situation where you're tossing one die. You agree? So each outcome has probability 1 out of 6. And so what's the expected value? It's the number on the die multiplied by 1 over 6. For each of them. For x and for y, they are symmetric. That's why we get the 2 here. So it's 2 times the expected value of x. So it's what? I can factor out the 1 over 6. And the summation of k from 1 to 6, it's 6 times 7 divided by 2. So this is here. 6 times 7 over 2 times 2 times 1 over 6. And the answer is 7. Everybody says that? Right, make sure that you understand that the sample space in this case can be modeled as a pair of coordinates. So X is acting on a sample space where each outcome is a pair of coordinates. S is the outcome on the first die, and T is the outcome on the second die, and X is just the projection of the first coordinate. And Y is the projection of the second coordinate. It's a projection map. Okay. Now, if I had n dies, then the expected value is still the sum. Right, and then I have that simply that it's just n multiplied by symmetry, it's n multiplied by the expected value of just one of them. So we have n times 7 over 2. All right, clear? Another example. An experiment consists of n independent trials. Each trial is a success with probability p. Find the expected number of successes. We're going to do that in several ways. You understand, guys? So suppose the trials are, let's say, a person throwing a basketball, right? So how many, on average, how many, what do you call it, goals or hoops or whatever you call that thing, when you are getting the basketball in? If you play, let's say, 10 rounds, how many successes will there be? Shots, okay, thank you. So how many successful shots on average? We're going to do it in several ways too, because it's an important observation.
So it would be 1 out of 10.
Well, that depends. That depends on what's the probability of success, right? How good you are at throwing hoops. If you're very bad, it could be less. If you're very good, it could be 10 out of 10, right? All right. So how do we do that thing? So first, guys, I'm gonna do that using old ideas, new ideas, okay? So first, let's observe what we remember about probability. Intuitively, we can do the following. How do we know the probability? How do you know how good somebody is, right? So let's say if my probability of hitting or shooting a hoop is, let's say, 1 in 100. How do I know that? Well, I have to throw the ball many times, and then you will see that you would notice that the ratio of hits divided by total trials approaches 1 over 100. Yes, and that's what this is doing. So P is the limit as you push the number of trials to infinity. Numerator is the number of successes divided by number of total trials. That's our frequentist idea of probability. This ratio is giving us, in essence, an idea of what's probability. Good. So if M is very large, the probability is about number of successes divided by total number of trials. Right? So the total number of successes will be M multiplied by P. I just multiply this number by M and I get total number of successes if P is known to us. Do you agree? In other words, if somebody is shooting is shooting with success 1/2, that means that if he does 1,000,000 shots, then about half of them will be successful, right? Now, suppose that the experiment is replaced by a large number of repeated large number of times k. So the total number of trials is k multiplied by n. Okay. So then total number of successes divided by, now you understand that we are considering batches of n, right? Batches of n, right? So in other words, we have one experiment consists of doing the procedure n times, and you want to know how many we get through those n times. You see, this is just unqualified. Just do it again and again and again. But now in the ratio where we are interested, we consider batches of n. So if I perform the total number of trials where I threw a hoop is k multiplied by n. And therefore, the total amount of success is k times n times p. Do you agree? Where k times n, where n is this fixed number and k is huge to make k times n very large. Are you still with me? Okay, this is then the total number of successes. Now, the number of experiments I don't divide by k times n, because that means the number of single shots. My experiment is a batch of n shots. Yes, batch of n shots is one experiment. So what do I divide by? I divide by k, because how many times did I repeat the n shots? K times. So k and p divided by k gives me n times p, where k goes to infinity. So that's intuitively deriving that result n multiplied by p from frequency's interpretation of probability. You understood it? I'm not sure if I explained anything clear today, guys, but I hope enough. Clear enough? Please confirm if you understood the intuitive explanation, yeah? Right, it's just how I ordered. I mean, how many shots I took altogether, k times n. But I don't divide by k times n because I'm not interested in the success of one shot. I'm interested in how many successes I have per n shots. So I divide by k to parcel into n experiments. So the answer should be n times p. Yes. Now we can verify that using expected value of sum equal to sum of expected values in procedure B. I can label xk to be equal to 1 if kth trial is successful and 0 otherwise. You see what happens? So I have a string, and how many total successes I have is each trial either produces 1 for success or 0 for failure. And I just add up over all the ones and zeros, and I get total number of successes per game. You understand? So those x's, what do? They label any particular. If I have n, if I take n shots, if I perform the experiment n times, but when the experiment consists of performing the same procedure n times, then I have codes like 0, 0, 0, 0 means all failures. 1, 1, 1, 1 means all successes, right? And then what I have is that each xk just looks at that string and it gives me 1 or 0 depending on success or failure. So the expected value is the sum of the expected values. Now, what's the expected value of each one of them individually? The expected value of x1 is simply 1 times the probability of success plus 0 times the probability of failure. So it's just p. Right? And it's very clear that there is symmetry here. So x1 will have the same expected value as x2, as x3, etc. Right? They all have the same expected value. Here is a new example, guys. So you understood how I use this, guys. I use the additivity of expected values, a very, very useful tool, and one that you want to get familiar and comfortable with as quickly as possible. Now, suppose that we have this new question. A new drug is tested. Out of 10 men and 10 women volunteers, a sample of 10 people is randomly chosen to participate in trials. What's the expected number of men in the chosen sample? I made this very simple so that you can already, without any calculation, guess what the number will be. We have 10 men and 10 women. Yes, a sample of size 10 is chosen. How many men do you expect to see on average? Very good. So a lot of you see intuitively that in this situation it will be 5, but that's only because there is a very nice symmetry here, right? There is no, if each individual is selected randomly, there should not be any preference for men and women, and therefore half of the sample should be men, half of it should be women on average, correct? How can you prove that? Now prove it that you're, because I could have made it not symmetric and that would be not obvious. Right, intuitively we say half of the participants, so you just took 1/2 times 10 and got a 5. So intuitively it was obvious. So how can you prove that this will be the situation? Okay. Okay, Jennifer, Sarah, and Fnum. Let's guys first see how would it happen if I did not observe additivity of random variables, the expected value of sum equal to sum of expected values. Suppose I were not aware of the fact and try to do it directly. Just look what happens. So let X be the number of men in the sample. Alan, you say the ratio of men to total multiplied by men. Be careful, I think multiplied by the size of the sample, I think. So let's see what would it be if I just decide to deal with the full sample space and not break it down, and see how difficult would that calculation be. So X is 0, 1, all the way to 10, right? It could happen that randomly I chose no men, or 1 man, or 2 men, or all the way to 10 men. Do you agree? So X here is a random variable that gives me total number of men in my sample. So the expected value by definition is what? It's the number k, right? The number k. And if I have k men, that means out of 10 I chose k. And out of the remaining 10 women, I had chose 10 minus k women. Do you understand this numerator, guys? And this is just 10 choose k times 10 choose 10 minus k divided by 20 choose 10 is the probability of getting k men, right? The probability of getting any particular sample of people, it's 20 choose 10, right? 20 choose 10 possibilities for the particular sample of people. Yes. Now success means that I have k men, which means which particular k men. There are how many ways can I get k men? 10 choose k times 10 choose 10 minus k women. That's how many ways I can have k men. Yes. And you see, I put a box around k times 10 choose k because I'm going to try to modify this. I know combinatorial identities, right? Look at what it looks like. So this expression looks like first choosing k jurors and then choosing the leader, choosing k people and then choosing the leader. Instead, I can choose the leader first, and then of the remaining 9 people, I join the k-1 committee. Do you agree? So you see this red box is the same as that. I can of course upgrade k equal to 1, at k equal to 0, this is 0. So I can begin the summation where k is equal to 1 to 10. Do you see how those 2 red boxes are the same? That's a combinatorial identity. Yes, of course. Look at this box. You should realize it as an instance of something we studied when we began with combinatorics. Yes? Basic combinatorics, guys. And what do we see? This means what? This means out of 10 individuals, choose a group of k and assign a leader. So you can first choose the committee and then assign a leader. Or you can first assign the leader and then choose the committee from the remaining ones. The committee is of size k. So either you assign the leader and adjoin the followers that are k-1 followers, or you first choose the committee and then from within the committee you pick the leader. So the rest red box and that red box must be the same. Yes? Now here I say, okay, let j be equal to 10 minus k. So this will be my j. If this is my j, I just reparameterize. If this is my j, then j begins, well, I can just look at what it can be, right? If k is equal to 10, j will be 0. And if k is equal to 1, then if k is equal to 1 over here, then j would be 9. Right? I'm just relabeling. So this is what? So this is 10 choose j. Now j is updated as the sum from 0 to 9. Now what is this thing here? This is 9, and this is then 9 minus j. K minus 1 is simply, look at it, it's very easy from here, right? Just solve for k. K is equal to 10 minus j. So this is 10 minus j instead of k, and then what you have is 9 minus j. Agreed? You understand what I do, guys? I'm just relabeling. Yes? And then I see this for the summation. Now what is the summation in the numerator? I can just look at it. Look at it here, guys. How is j 0 to 9? Well, look at it, right? K is 1 to 10. If k is 1 to 10 and 10 minus k is j, so 10 minus 10 is 0 and 10 minus 1 is 9. They're just in reverse. Where k is 1, j is 9. Where k is 10, j is 0. So I can just rewrite the summation in this form. So what do we have? We have now this summation. And now this is what you should recall. This is just to remember in blue, guys. Remember that now another identity, j is equal to 0 all the way to n, n choose n minus j, m choose j, is the same as n plus m choose n. This is an identity that you should be familiar with. It means that if I have 2 categories, men and women, I can calculate the number of ways to pick n individuals as how many individuals were picked from category M, and then the remaining individuals have to be picked from category N. The denominator is this terms must sum to N. Yes, so that means, look at it, guys. We have 9 of this category, 10 of that category. You see what happens here is that this is 9 minus j and this is j. We have to choose 9 individuals. I mean, forgetting about the initial meaning, I just look at the combinatorics and I see that this is just saying we have 2 categories here. This is category 1 and this is category 2. and we choose a committee of size 9 from 19. So it's 10 times 19 choose 9. So this full summation reduces to 19 choose 9. Do you see that? So it's 10 times 19 choose 9. Now what else can I do here? I would prefer this to be 20. So I write it as 20 times 1/2. So it's 20 times 19 choose 9. And what is this? This is now the same thing, guys. 20 times 19 choose 9 is the same thing as 10 multiplied by 20 choose 10. Yes? You don't forget your combinatorics. So what do I have? I have this.
Professor, you have a like this formula. Yeah, sorry.
Now good?
Yeah, yeah.
Mm-hmm. So what do we have? We have 1/2 times 20. So again, we can simplify 20 choose 10 here, and we have 10 over 2, and we get 5. Right? So that was not easy at all, right? We still kind of use clever identities to move through, but it took us a long time. Do you agree? And I'm not sure, even as it took us a long time, if you followed what I did. I manipulated this expression, made it simpler, used 2 combinatorial identities, used some of the combinatorial identities twice, until I was able to reduce it to the simple number 5, which of course, because of symmetry, I knew immediately without any calculations here. Yes? Now all you have to do, guys, is just recall this identity, understand just that I relabeled, and then understand how I took this summation. Here I try to remind you of the formula and reduce the summation from 0 to 9 of 9 choose 9 minus j, 10 choose j, how I translated it to 19 choose 9. It's the same thing. You understand? This full summation is the same as 19 choose 9. And then I applied that same idea I did here, but in reverse, because now I have 10 times 19 choose 9. And I realized, oh, I want to have here a 20. 20 times 19 choose 9 can be replaced by 10 times 20 choose 10. Yeah? Because now it's the same as this original committee, just I use the reverse of it. I go from this to that in reverse. Yeah? And then there was a 1/2 here, so then this crosses out, and then we have just 10 over 2, which is 5. Naturally, so exhausting. Now here is how you can do it instead. If you understand the additivity of the expected value, you can just simply say the following. Well, suppose that that we choose those people in order. Remember, we can do the probability by either choosing the people right away or picking them one after the other. We proved at some point that the result will be exactly the same type of randomness. So then I can say, well, let xk be 1 if the kth person chosen is a man and 0 otherwise. So the expected value is the summation of the xk from 1 to 10, which according to expected value rules is always the sum of the expected values. So it's the summation from k1 to 10 of expected value of xk. Now they are exactly the same. If I look at each random variable separately, but ignoring the others, it's exactly, it's having the same exact distribution, exactly same expected value. That is, for instance, the third person chosen, right? The third person chosen is equally likely to be a man or a woman. It's equally likely to be any of the people, right? There is no preference to who is number 3. It can be any one of the available people. And what do we get? We get that, that the expected value of x1, for instance, is 10 multiplied by 10 choose 20. 10 divided by 20. You see why? Because we have 10 men, and the 10 men that can be person number one out of 20 individuals that could be person number one. They're equally likely. So I just see that it's 10 times 10 divided by 20, which is 5. So it's a very, very useful to understand, guys. You have to really have a very intuitive understanding of the expected value and how the additivity works. What makes it work? So here is a matching problem, guys. Remember the matching problem. So you have those n gentlemen, and each of them has a hat, and they pick their hats at random. And we asked for the probability that not a single one of them picks his own hat. Yes. Now I'm interested in the average number of hats that those people will pick that are their own. Do you understand? On average, how many hats will each individual? How many individuals will pick their own hats if you have n individuals? Is that clear? The question. So if I have 20 individuals and 20 hats, and each individual picks a hat at random, how many on average? How many individuals on average will pick their own hat? You can do it with n. All right, what's happening, guys? Matching problem. You understand what happens here, guys? So each randomly picks a hat. The probability we calculated once, it was the probability that nobody picks his own hat is e to the -1, if you remember, Jack. All right, so let's do it together, guys. Here is how we can go about it. Well, let xk be the outcome on the, it's equal to 1. In other words, it's the outcome for the cave person. It's equal to 1 when cave person picks his own hat and 0 otherwise. Yes? So our expected value is the sum of those variables, right? So how much x1 is giving, how much x2 is given, all the way to xn. Clear? Now, when viewed individually, they are identically distributed. So what's the probability that person K picks his own hat? I mean, he can pick any hat. Individually, person number K can pick, there is no preference. It's either hat 1 or 2 or 3 or all the way to n, with only one outcome being hat number K. So it's 1 over n is the probability that this person will pick his own hat. So it's 1 times 1 over n plus 0 times n minus 1 over n. So it's just 1 over n. The expected value of each xk is 1 over n. And the summation is just it's just the sum of each expected value. Since they have the same expected value, it's n times 1 over n, and the answer is 1. Do you see that? So on average, guys, and it's pretty interesting, no matter how many individuals you have, do you see what this means? We didn't say how many individuals you have. If you have 2 gentlemen playing this game, on average, the number of hats picked by their owner is 1 person picks, right? Only 1 person on average picks his own hat. And if you have billions, it's the same thing. On average, exactly 1 person picks his own hat. What is next? Next question, you mean, no? Okay, I see. Oh, cool. Let's see. Maybe all right. Here, guys, is the next question. So urn contains n balls, k of which are blue and n minus k are red. And we pick a sample of size m, which is smaller or equal to n. It's randomly drawn. I want to know how many blue balls are we expecting? How many blue balls? You see, k are blue and n minus k are not blue or red, whatever, right? Sample is of size m. On average, how many blue balls will we see? Okay. Mm-hmm. All right, good. Same idea, guys. Same idea gives us the result. So we can imagine, you see how we can imagine it. X1 is equal to 1 if the first drawn ball is 1. And it's 0 otherwise. And then so we have how many x's? We have m of them for the size of the sample, right? First x1, second is x2. And the random variable is the sum x1 all the way plus 2xm. The expected value of the sum is the sum of the expected values. And the expected value of an arbitrary ball xj. You see, guys, because there is randomness, you see what you do here? Xj, naturally the results that came before will influence the likelihood of j being blue or not. But individually, if I ignore everything else, the JF ball is equally likely to be any of the available n balls, right? So only k of them are blue and n of them in total. So k out of n is the probability of getting a blue ball on the JF attempt. Yes. So the expected value of xj is 1 multiplied by the probability, which is k over n, plus 0 multiplied by the probability n minus k divided by n. You agree? So it's just k over n. That's the expected value of xj. And so the summation here, because they're all the same, it's k over n for each individual j. It's just k over n multiplied by m. Good? So I hope you think it's easy, but not just because you are able to carry in these examples, but you understand why the expected value can be broken this way. All right. So here is the next example, guys. Let's see how we do in this situation. So urn initially contains 1 red and 1 blue ball. A ball is randomly extracted and then replaced by 2 balls of the same color. So we have 1 red and 1 blue. We extract 1 and replace by 2. Okay. And then we have the following situation. Let X be the first time blue ball is removed. Right? So a blue ball is either removed on first or second or third attempt. Okay, we continue doing that until we remove the first ball. So please calculate the probability that X is equal to K and then calculate the expected value. Okay, the expected value. What's the probability that X is equal to K? In other words, what's the probability that first time I remove the blue ball on the KF trial? 1, the probability that I will remove it for the first time on trial number 100 is probability 1. Unlikely, right? You understand, guys? For the first time. So here is the situation, right? You can just calculate it as a product. So if I remove it for the first time on the cave trial, then the previous trials were not removing a blue ball, which means first I remove the red ball, then the probability that I am not going to remove the blue on the next trial is 2/3, because now I have 2 reds and 1 blue. Then it's going to be 3/4. Do you see why? 3/4, because you add 2, right? You add 2. And each time you remove a ball, you bring another extra. So you add 2. Now you have 3 red balls, and altogether 4. Then you have 4 red balls, 5 altogether, all the way until the k-1 attempt. It's failure. So you have k-1 red balls by that time, and k balls in total. Finally, you do remove a blue ball, so it's 1 over k plus 1, right? Because that's the total number of balls. Now you can simplify everything here. You can see that it's 1 times 2 times 3, so it's k-1 factorial over k plus 1 factorial, and that result is 1 divided by k times k plus 1. Yes? Now, what's the expected value, guys? What do you think? The expected value. In other words, on average, how long will it take you to remove a blue ball? The blue ball, why? I mean, no, the value of 1 here, it means the number of trials, right? So your success is you remove balls until you carry this experiment until you are successfully getting a blue ball. That's when you stop, okay? On average, how long will it take you to stop? You see, we just obtained the probability, right? The probability that you will stop after by the KF drawing is 1 over k times k plus 1. So the probability you stop by the first drawing, it's 1 over 1 and divided by 1 over 1 times 2. So it's 1/2, obviously, right? Good. So we have a probability that will stop after a particular drawing. On average, how long will it take you to carry this procedure?
I got a question.
Yes, go ahead, James.
So you said how long would it take?
Yes.
I mean,
How many drawings, to be precise, right? I'm not sure how long, I mean, but how many drawings? Is it on average 1 drawing, 2 drawing, 3 drawing, 10 drawings? How many drawings on average will it take to withdraw the first blue ball and therefore stop this process?
I mean, hopefully, like after you do it like once or twice, I guess. But it should
saying
be.
on average it will take you 2 drawings.
No, it's not gonna take 2 drawings because it goes to infinity. But you be hoping that. Never mind, forget about it.
What is going to infinity? That's the question. You say it, but the it is not clear to me.
I mean, the amount of the amount of drawings
Well,
goes
I mean,
infinitely.
so you see, so you understand, guys, what it's definitely possible that the first time you would draw the ball is on the millionth attempt or trillionth attempt, but on average, how much will it take you? Look at it, guys. So here I just verify that the probabilities do add up to 1. It's the summation of 1 over k times k plus 1. This infinite series, it adds up to 1. I just verified. I summed up the probabilities from 1 to infinity. The probabilities add up to 1. However, the expected value, guys, is the summation from k1 to infinity of k times 1 over k plus 1 over times k. And the k's cross out, and that's the summation of a harmonic series. Do you recognize it? And harmonic series, they diverge. It's a divergent series, which means, and I'm not sure if it surprised you or not, guys, the average number of drawings that it will take to stop this game is infinity. You understand? So on average, it will take you infinite drawings to end the game. Isn't it strange? Even though the probability that you will stop at a finite amount of time is not 0, right? You just, the probability you stop at a finite amount of time, it's say the probability you will stop after the first drawing is 1/2. 1/2 of the times you play this game, you will be done after the first drawing. Do you understand? So the game terminates 1/2 of just half of the games. If you played 1 billion games, about half of those games will terminate after the first drawing. Yet on average, it will take you infinitely many drawings to end the game. Does it surprise you? No? Because you are kind of beyond surprise by now, right? Yes, somebody raised the hand. Jack, go ahead.
Can you explain how 1 over k times k plus 1 equals 1 over k minus 1 over k plus 1?
That's called partial fractions. Partial fractions. We can explain after once the class is over, which is pretty much now. This is partial fractions, and you can just notice. First of all, I knew the answer will be 1 because probabilities add up to 1. I could have just reasoned probabilistically that the answer has to be 1. If I calculated probability correctly, the sum of possibilities is 1. Probability add up to 1, right? So I knew the answer will be 1, but I just used algebra to verify. And this is a over k plus b over k minus 1 plus b over k plus 1, and it ends up being this. Okay, I can show you how to do that. And then I just take the limit, and I can see things cancel out, and good. And so I'm not sure, guys, so it's hard to surprise or entertain you, right? So you understand, on average, it will take infinitely many trials to, the game will on average be going forever. Do you understand? Each time you play the game, it will be finitely many times. I can guarantee it, because the probability that the game lasts forever is 0. But on average, it will take you infinitely many trials to end the game. All right. So I will then dismiss you, I suppose. If you look at me like, okay, sure, right? No problem there. Take care, guys.